100%. That is how much of Mars has been mapped from orbit at 100 meters or finer. You have grown up with that map. 26%. That is how much of Earth's own seafloor has been mapped to modern standards. Less than 1%. That is how much of the deep ocean any human, camera, or probe has ever directly seen. You're above the third number right now. Most of the heat we have trapped on this planet is stored in that water. The cables carrying this video run along its floor. A coral down there has been alive for 4,000 years, in total darkness, while you have been watching screens. That is the largest living space on this planet, mapped mostly in shape, almost entirely unseen by light. You grew up on a planet that thinks of itself as known. The maps are catching up to that belief. The cameras have barely started. What we are missing is not the point. What we are choosing not to see, that is the point. A map is a guess that has been measured. A witness is someone who has seen. We have many maps of the deep ocean. We have very few witnesses. This distinction is not pedantic. It is where the entire story turns. When the topographic map of Mars was first published, it covered the whole planet at 230-meter resolution. By 2018, every square kilometer of Mars had been imaged from orbit at 100 meters or finer. A child can fly through Valles Marineris on a phone in a living room. The shape of that planet is, in a public sense, settled. Earth's seafloor is not. As of 2024, only about 26.1% of the global seafloor had been mapped to modern bathymetric standards. The remaining three-quarters is currently approximated through satellite gravity measurements at roughly 6-kilometer resolution. That is not a map. That is a fog colored in. The international project Seabed 2030 is working to close the gap, and the percentage moves every year. But for now, the floor of the ocean we live on is mostly an estimate. And mapping, even the high-quality kind, is not seeing. A bathymetric map shows you where the mountains rise and where the trenches fall. It tells you the shape of a place. It does not tell you what is on it. A topographic line cannot describe a coral. A depth value cannot describe a vent. A grayscale grid cannot describe a 30-armed sea spider walking across a sediment plain. Direct observation, putting a human eye, or a camera, or a fiber optic ROV light onto the sea floor, covers less than 1% of the deep ocean. Less than 0.6% by some measurements. The lit zone is a few kilometers of patches and transects threaded through a wilderness larger than every continent on Earth combined. This is the difference between a map and a witness. A map can be drawn from a distance. A witness has to be there. Hold that distinction. We will return to it more than once. To understand why the deep ocean is so unseen, you have to understand what it is. The deep ocean begins, by convention, at 200 meters down, the depth at which sunlight effectively fades from the water column. Below 200 meters, photosynthesis stops working. Below 1,000, almost no light remains. Below 4,000, the water has been disconnected from the surface, in some cases, for 1,000 years. There is a vocabulary for these zones. The bathyal stretches from about 200 meters to 3,000, twilight giving way to dark. The abyssal lies between roughly 3,000 and 6,000 meters, true dark, near freezing water, sediment-blanketed plains. The hadal, named after Hades, the Greek god of the underworld, begins at 6,000 meters and continues into trenches that reach below 11,000. Most of Earth is in this category. Abyssal plains alone, The flat, dark, sediment-blanketed floors between 3,000 and 6,000 meters cover more than half of the entire surface of the planet. They are the most common landscape on Earth. They are also the least known. By volume, by the actual amount of three-dimensional space in which an animal can live, the deep ocean accounts for roughly 98.5% of Earth's total. The land, the air, the rivers, the lakes, the sunlit surface waters, every garden and city and forest combined make up the remaining 1.5%. You live in the 1.5%. The other 98.5% is dark. At 6 kilometers down, the pressure is roughly 600 times what you feel at the surface. In the deepest trenches, that pressure rises to more than 1,000 atmospheres. Steel can implode. Glass can crack. The temperature is just above freezing. Sound moves slowly. Light does not move at all. Down there, every step that engineering takes is a problem of pressure first. A camera, a microphone, a wire connector, a battery, a motor, a weld seam on a sample chamber. All of them have to survive the same thing the seafloor itself survives every day for hundreds of millions of years. The deep ocean is not a place we are visiting reluctantly. It is a place that resists our visit. That difference matters. There is a simple physics reason that the deep ocean is harder to image than Mars. Electromagnetic waves, light, radio, radar, are how we see almost everything we know about the rest of the universe. A satellite in orbit around Mars uses radar and reflected sunlight to map terrain. A telescope catches photons from a galaxy that emitted them 10 billion years ago. Visibility for almost the entire universe runs on photons. Photons do not run far in seawater. Visible light is mostly absorbed within the first few hundred meters of the ocean. Radar and radio waves are absorbed even faster, in some cases within centimeters. By the time you cross the shallowest border of the deep ocean at 200 meters, the electromagnetic spectrum is, for any practical mapping purpose, dead. What is left is sound. We map the deep ocean primarily with multi-beam sonar, wide swaths of acoustic pings sent down from a ship's hull, bounced back from the floor, timed and reconstructed into terrain. It is, conceptually, the same method a bat uses inside a cave. Different scale, same physics. Sonar gives us shape. It does not give us color. It does not give us life. It does not, by itself, tell you that there is a coral on the ridge, or a vent at the base of the seamount, or a pile of fish bones beside a dead whale fall. For that, you need a camera and a light, and you need to put both physically there. And every time you put a camera physically there, you can only light up a few square meters at a time. This is the second reason the deep ocean is so unseen. It is not just that mapping is incomplete, it is that mapping was always going to be the easy part. Communication is the same problem turned inside out. To talk to a robot at 1,500 meters depth, you cannot use radio. You have to use sound. And sound moves at roughly 1,500 meters per second in water. Every command travels for 1 full second to reach a robot 1.5 kilometers down, and another full second to come back. 2 seconds of dialogue lag in an environment where the wrong move can cost you the vehicle. That signal lag is, in spirit, the same lag that haunts the operators of the Mars rovers. There, the lag comes from distance. Here, it comes from the medium itself. A Mars operator works around the lag with autonomy. They build a robot that decides on its own what to do when a wheel slips. A deep-sea operator now does the same. The abyssal robot has to think for itself because the operator on the ship cannot answer in time. This is one of the moments where the abyss and the cosmos start to look the same, but not for the reasons most people assume. We will come back to this. The popular image of the deep ocean, when it has one at all, is empty. Cold, dark, pressurized. A long, slow, sediment-blanketed nothing. That picture is wrong. The deep ocean is the largest habitat on Earth. It is also one of the most biologically rich. Of the marine species that have been formally described, given a name, classified, registered in the literature, there are roughly 230,000. Of the marine species that are estimated to exist, the most defensible scientific number is that we have described about 10%. The other 90% remain unnamed. Unnamed does not mean unimportant. It means we have collected them. We have looked at them through microscopes. We have, in many cases, photographed them. And we have not yet done the slow, technical work of formally describing them, assigning a species, comparing to relatives, publishing. In the Clarion-Clipperton Zone, a stretch of abyssal plain in the Central Pacific that has become the focal point of deep-sea mining interest, the ratio is sharper. Of the animal species that have been collected from that single region, only about 8% have names. Some of these organisms are very old. The oldest deep-sea black coral on record has been dated at 4,265 years. That coral was already 1,000 years old when the Great Pyramids were under construction. It has spent every year since then in total darkness. It is still alive. Others are very strange. There are tube worms at hydrothermal vents that grow more than a meter long without any digestive system at all, fed by chemosynthetic bacteria living inside their tissue. There are fish in the Hadal trenches with bodies that flex under pressures that would crush a steel sphere. There are bacterial communities living inside the rock of the seafloor itself, in cavities that may extend kilometers into the crust. There are organisms, the deep-sea pyrosomes, the cold seep mussels, the predatory glass sponges, whose body plans look like guesses someone made about life on another planet. The deep ocean is not empty. The deep ocean is the rule. What you are used to, air, sunlight, plants, is the exception. This is the point at which most documentaries would congratulate you on caring. We will not. The species count is not a lesson in wonder. It is a problem of ledger. We are preparing to industrially exploit a wilderness in which we have named less than 10% of the inhabitants. In some specific zones, less than 10% of that. That is not a moral verdict. It is a fact about the order of operations. For most of biology, the energy that runs life comes from the sun. Photosynthesis at the surface, plants on land, phytoplankton in the upper ocean, converts sunlight into the carbohydrates that, somewhere along the chain, every animal eats. The deep ocean breaks that rule in two different ways. The first is dependence. Most life in the abyssal zone still runs on the sun, but indirectly. Organic matter from the sunlit surface, dead plankton, fish carcasses, fragments of coastal vegetation, drifts down through the water column as a slow, continuous fall. Marine snow. The deep, in this second, is a scavenger zone, fed by crumbs from a world it cannot see. A research submersible called Alvin descended along the Galapagos Rift and found something the entire field had been told not to expect. At about 2,500 meters depth, in total darkness, around the cracked spine of a mid-ocean ridge, there were animals. Tube worms 2 meters long, clams the size of dinner plates, crabs, vent shrimp, dense colonies of life clustered around fissures in the seafloor where superheated, mineral-rich water was venting out of the Earth's crust. They were not subsisting on marine snow. They were thriving in dense, complex colonies on something else entirely. The energy that ran those colonies was not the sun. It was the chemistry of the planet itself. Bacteria around the vents were oxidizing hydrogen sulfide and methane, chemicals leached from the rock by hot fluid, and using that energy to build the carbon-based molecules of life. Chemosynthesis, a second way to be alive. Hydrothermal vent ecosystems are tiny by area. Active vent fields, taken together, cover less than 50 square kilometers worldwide, less than 0.00001% of Earth's surface. But what they tell us is enormous. They tell us that a planet does not need a sun to host life. It needs heat. It needs water. It needs the right chemistry. And it needs time. There is also, possibly, a third surprise, much newer and still being argued about. In recent years, evidence has emerged that the polymetallic nodules scattered across some abyssal plains may be producing oxygen abiotically, in total darkness, through electrochemistry. Dark oxygen. Oxygen without a single ray of sunlight, generated by minerals on the sea floor itself. If that finding is confirmed at scale, and it is currently emerging evidence, not a settled law of nature, it would mean the basic equation of habitability has another door we did not know about. It would also mean the same nodules being targeted for mining are doing something we do not yet fully understand. This is also the moment in which the search for life beyond Earth changes shape. Until vents, the standard astrobiological imagination was sunbound. You looked for warm, rocky planets in the right orbital zone. You looked for atmospheres. You looked for surfaces that liquid water could rest on under sunlight. After vents, you can look for something else. You can look for a moon in the cold outer solar system, with a subsurface ocean kept liquid by tidal heating and in contact with rock. You can look for hydrothermal chemistry in a place no sun ever reaches. That is, more or less, exactly what we now believe Europa and Enceladus might be. Cassini, flying through Enceladus's south polar plumes, sampled water ice, organic molecules, and chemistry consistent with active hydrothermal activity below the ice. Europa, beneath roughly 20 kilometers of frozen crust, is suspected to hold a saltwater ocean larger than every ocean on Earth combined. The strangest discovery in the deep was not the darkness. It was the life inside it. Life without sunlight. Life without a sky. Life built around heat, pressure, and chemistry. And that opens a question this video cannot finish answering. If life can be built around a vent on the floor of our own ocean, where else in the solar system should we be looking? What does it mean for Europa, for Enceladus, for Titan, for the dozens of other ocean worlds the next generation of probes is already being designed for? That is the conversation we will pick up in the next part of this series. If you want to follow it, subscribe and turn on notifications. For now, this part of the story is still on Earth, because before any probe drops through 20 kilometers of European ice, there is something we still need to learn. We need to learn how to see in the dark on our own planet first. There is a tendency, when discussing the deep ocean, to frame it as a place of curiosity. That framing is wrong. The deep ocean is not a curiosity. It is, in measurable terms, the apparatus that keeps the surface world habitable. Begin with heat. Since industrial humans began burning fossil fuels in volume, we have trapped a large amount of additional energy in the climate system. Most of that energy did not stay in the air. About 90 to 93% of the excess heat from anthropogenic greenhouse gases has been absorbed by the ocean. The atmosphere, the place where weather happens and where you actually live, has absorbed less than 10%. Without that uptake, the surface temperature record of the last century would look catastrophic in ways the human story has never had to absorb. Heat we recognize as bad in the air is, by mass, vastly worse in the water. The ocean has been quietly absorbing it. It has not done so for free. The same uptake is acidifying the surface ocean and warming the deep one. A coral that has been alive for 4,000 years is now living in a chemistry that is changing inside a single human generation. Now move to carbon. Earth's ocean stores roughly 40,000 billion tons of carbon. That is more than 50 times the carbon in the atmosphere. The mechanism is, in part, a slow biological pump. Surface phytoplankton fix carbon dioxide, die, sink, and end up locked in deep waters and sediments on geological timescales. Combine those two facts and the picture is plain. The ocean, and especially the deep ocean below the mixed surface layer, is the planet's thermal buffer and its largest active carbon vault. Now move to oxygen. A common popular claim is that rainforests produce most of the oxygen we breathe. The actual figure is closer to 2/3 of Earth's oxygen coming from the ocean, primarily from photosynthetic phytoplankton in the upper waters. The deep ocean does not produce that oxygen, but it is part of the system that holds the ocean as a whole. Disturbing that system is not free. Now move to infrastructure. Approximately 98% of all international telecommunications travel through submarine cables resting on the deep sea floor, not through satellites. Every transcontinental video call, every cross-border bank transfer, every cloud sync, every multinational stock trade, almost all of it hops along a fiber optic line about the thickness of a garden hose, lying in the dark on a sediment plain. A single submarine landslide can isolate a continent's economy. Turbidity currents, slurries of sediment moving along the floor, have been recorded traveling more than 1,000 kilometers and snapping cables along the way. The cloud is not in the sky. The cloud is in the dark. Now move to hazards. Most of Earth's most dangerous tectonic events, large earthquakes, large tsunamis, originate at submarine plate boundaries. Mapping the seafloor at high resolution is not just scientific. It is the basis for tsunami forecasting. The shape of a submarine ridge tells a wave where to go. The shape of a continental shelf tells the wave how tall to be when it arrives. Without those maps, that prediction is degraded. You do not live above the deep ocean as a tourist. You live above it as a beneficiary. The system that buffers your climate, locks your carbon, carries your data, and warns of your tsunamis is largely unmapped, almost entirely unseen, and changing. That is the part of the story that has stakes. There is a particular irony in the way the abyss has been treated as the opposite of space. The cultural narrative is straightforward. Space is the future. Space is what we point our money and our mythology at. Space is the next frontier. The deep ocean, in this telling, is a kind of nostalgia object, a place we missed, a planet we forgot to finish exploring before we left. That story is wrong in a specific and useful way. The deep ocean is not the opposite of space. It is, in operational terms, its rehearsal room. NASA does not pretend otherwise. For more than 2 decades, the agency has run a program called NEMO, NASA Extreme Environment Mission Operations, that places astronauts inside Aquarius, an undersea research habitat off the Florida Keys, for missions that simulate space station operations and planetary surface activity. It also runs Subsea, Systematic Underwater Biogeochemical Science and Exploration Analog, which uses Earth's hydrothermal vent systems as direct analogs for missions to the icy moons of Jupiter and Saturn. These programs are not metaphors, they are training. Astronauts work tools they will use on long-duration missions. Scientists rehearse the kind of life detection protocols that Europa Clipper, Enceladus mission concepts, and proposed Titan probes will need. Engineers test sampling techniques in conditions where contamination control matters as much as it will matter on an icy moon. The technical synergies are concrete. Both environments demand high-reliability robotics that operate beyond physical reach. Both require autonomous decision-making under signal lag, minutes for Mars, seconds in the abyss. But the cognitive structure is the same. Both need life detection instruments capable of distinguishing biological signals from background chemistry without false positives. Both demand engineering that survives extreme conditions over long periods, with no opportunity for repair. When you watch an underwater robot carefully approach a hydrothermal chimney, sampling fluid through a manipulator arm controlled at a delay, you are watching something extremely close to what the next generation of planetary missions will do. The pressure direction is reversed. The moon probe will work in vacuum, the seafloor crawler in 500 bars of compression, but the cognitive architecture of the task is almost identical. This is what makes the comparison between Mars and the deep ocean interesting. It is not a competition. It is a continuity. Mars gives us distance. The ocean gives us depth. Both are training us for the same kind of careful, restrained, evidence-led exploration. If we do this well, we will arrive at the icy moons of the outer solar system not as tourists, but as a species that has learned how to look without breaking what it is looking at. We will have practiced. If we do not, we will arrive at Europa with the bad habits of an industry that mined an environment it had not understood. This is where mapping stops being enough. This is the moment in the story where the temptation is to be melodramatic. We will not be. The Clarion-Clipperton Zone, a Pacific abyssal plain roughly the size of the continental United States, is currently the focal point of a developing deep-sea mining industry. The seabed there is dotted with polymetallic nodules, potato-sized concretions of manganese, nickel, cobalt, copper, and a long list of rare earth metals. The metals are not abstract. They are real industrial inputs. They feed batteries. They feed wind turbines. They feed electric motors and grid storage, and the entire material backbone of the energy transition the world has, in principle, already chosen. Mining of these nodules is not yet at industrial scale. It is at the threshold. Permits are being negotiated through the International Seabed Authority. Test runs are being conducted. Equipment is being built. Industrial-scale dredging, when it begins, is not subtle. A single trailing suction hopper dredge can dredge more than 100,000 square meters of seafloor per day. The disturbance is not only the area scraped, it is the sediment plume thrown into the water column. It is the noise carried for hundreds of kilometers across an environment that evolved in near silence. It is the destruction of habitat structure that may take geological timescales to rebuild, measured in thousands of years, not decades. Two facts deserve to be held in the mind at the same time. The first is that the metals being targeted are real industrial inputs to real climate solutions. Mining them on land also has its own ecological and human cost. There is a defensible argument that nodule mining, done carefully, may turn out to be part of a transition we have already chosen. The second is that the seabed beyond national jurisdiction is, under the United Nations Convention on the Law of the Sea, the common heritage of mankind. It does not belong to any country. It does not belong to any company. It is, in the most literal legal sense, ours together, and obligations attached to that ownership. Combine those two facts with the earlier numbers, 90% of the species in the abyss unnamed, 8% in the CCZ specifically, and the situation is plain. We are deciding the fate of a habitat we have not yet finished cataloging. Not because we are reckless, but because the catalog is harder than the decision. This script is not going to tell you what to think about that. It will be honest about what is at risk, a quiet, vast, unwitnessed ecosystem that took the planet 4 billion years to assemble, being entered industrially in the same decade in which it is, for the first time, being mapped to modern resolution. The mapping is finally happening. The seeing has barely started. The mining is already at the door. We began with 3 numbers. We will end with a question. If you had to fully understand one frontier first, Mars or the deep ocean beneath us, which would you choose? And why does that answer feel harder than it should? Tell us in the comments. We read them. The reason that question is hard is that the framing was wrong from the start. The deep ocean is not the opposite of space. It is the same project, looked at from a different direction. The same instruments, autonomous robots, pressure-resistant samplers, sensitive life detection systems, apply to both. The same intellectual habits, restraint, evidence, careful sampling, contamination control, are required by both. The same philosophical question, where in this universe can life be built and sustained, is being asked in both. Mars made us look outward. The ocean is teaching us how to look at all. We have already mapped the surface of a dead planet 140 million miles away. We have not yet finished the map of our own. We have seen the dust of Mars in higher resolution than we have seen 99% of the floor of the world we live on. That is not a failure of priority. It is a clue about what exploration actually is. Exploration is not getting somewhere. Exploration is learning to see. The first place we will need to do that is here. The deep ocean is where we will rehearse what it means to be careful in the dark. It is where we will learn to map without breaking, sample without contaminating, and observe without illuminating more than we have to. It is where we will earn the right to go further. When the next probe drops through the ice of Europa decades from now, the engineers in that control room will, in a small but real way, owe their training to a coral on a ridge in the Atlantic that no human has yet seen. We are not, in any meaningful sense, choosing between the abyss and the stars. We are walking through both in the dark, with a single small light.